Okay, thank you very much. Let me start by thanking the organizers for organizing this wonderful conference. It's been great so far. So as you can probably suspect from the title, this has rather tenuous connection to space-time or string theory, although it was very much motivated by my wanting to understand the emergence of space-time in string theory. And it's going to be sort of a review of a strand of an idea that sort of started building up through these papers with various subsets of these collaborators. And the pivotal one was this highlighted one with Sergio Hernandez Cuenca and Max Rota, who was really sort of spearheading the program. Okay, so to motivate it, well, over the last decade or two, we have seen really exciting hints of some profound connection between the entanglement structure of a given quantum system and its physical behavior. So among the most tantalizing expectations is that entanglement somehow underlies the emergence of classical dynamical space-time. And well, early sort of hint of that was already with the holographic entanglement entropy proposal of relating this entanglement entropy to just an area of a bulk surface, extremal surface in the holographic context, and certainly has been much more substantiated. So one is then invited to sort of try to understand entanglement structure of the geometric states in the holographic context. So that's sort of the starting point. Now, when I say entanglement structure, that's a very vague term. The sort of, in quantum information theory over the last few decades, the concept that has been best developed is the measure of entanglement for pure bipartite systems. And the natural one there, as we heard very nicely reviewed earlier this week, is that of the entanglement entropy, which is the quantum version of the Shannon entropy. It's a von Neumann entropy and provides sort of a measure of the mixedness of the reduced density matrix. However, if you have continuum systems or quantum many-body systems, one wants to know more. One wants to know how different parts of the system interplay with other parts. And despite concentrated effort, the multipartite entanglement measures have been much worse understood or less well developed, partly because you can't use the power of linear algebra and to the effect, and the complexity of the description becomes much more severe. So many measures have been proposed, but there isn't a natural canonical one. So what one can do is retreat to, again, bipartite, entanglement entropy, but now between various partitions of the full system. And that quantity, you can construct things called multipartite informations that actually measure some aspect of this multipartite entanglement. So we will be working in just the regime of thinking about this, all possible entanglement entropies for all possible subsystems. Okay, such a collection, if you're given full system and specification of subsystems, the collection of these entanglement entropies is very naturally organized in a so-called entropy space, where the x's are the individual entanglement entropies, and we can then collect them into a quantity that's known, that we call entropy vector. And so the question here translates to a question in this context of what are all the possible entropy vectors that we can obtain in this holographic context for geometric states. Again, not all the entropy vectors are allowed. They're restricted by the so-called holographic entropy inequalities. And so they form a cone, a convex cone in this entropy space that has been dubbed the holographic entropy cone. So the goal of this sort of overarching program that I'm going to be telling you about is to sort of understand or explain this holographic entropy cone. But we'll actually retreat further, and what I want to focus on today is to tell you that, well, it seems that there's a great power to be gained from just not worrying about, how much two systems are entangled with each other, but just the binary information of whether they're entangled at all or not. Okay, so this concept of the pattern of correlation versus decorrelation between various subsystems is going to be the key player today. And we'll see, you might think that this is such a coarse-grained information that it can't possibly be very useful. It won't tell you very much. But in fact, we'll see that it reconstructs the entire holographic entropy cone in a very specific sense that I'll try to explain. And I have sort of begun to suspect or hope that it might actually extend well beyond holography. So the tools that we had used to sort of explain this were very much within holography, but I think it might actually be much more powerful organizational principle even beyond that context. All right. So to sort of explain that picture, I'll first give you a little bit of a background to put everyone on the same page, and then sort of describe what I mean by this. Okay, these words in the title, the marginal independence, and then try to give a geometrical picture of that, geometrical in the entropy space, by talking about this hierarchy of these various cones, and give you recent results, well, actually, results that are still work in progress on a specific quantity. Okay, so as we already heard very nicely explained by Jonathan and then Tadashi, entanglement entropy is the von Neumann entropy of reduced density matrix. And here I'll be making the same assumptions, same context as Tadashi explained yesterday. So assuming that we can talk about these things meaningfully. So in a holographic context, we imagine that we have some space, the boundary CFT lives on, and we can specify spatial subsystems. Each one has, associated Hilbert space for that subsystem, and therefore we can sort of talk about the entanglement entropies of, let's say, the region A, the region B, but also the region A, B, and so forth. So for n such parties, we get 2 to the n minus 1 independent quantities, the individual entanglement entropies, and we collect them into this entropy vector. Okay, so here I have given you the example for 3 subsystems, n equal to 3, but we'll find that it's very useful to think of sort of different values of various values of n, not fixed n a priori, and in fact look at or utilize the sort of structural relations for different various values of n. And ultimately, of course, one would like to understand it for arbitrarily large n. Of course, in practice, this is going to get tricky computationally because some quantities are sort of doubly exponential, so things get hard very quickly. Okay, so once you have these entanglement entropies, you can build up the sort of measures of the total amount of correlation. That's the so-called mutual information. Okay, so that's just the difference between the sum of the individual entropies and the composite entropy. And these things satisfy positivity and monotonicity under inclusion. So positivity is the famous sub-additivity inequality that the sum of this is bigger than the composite one. So mutual information is non-negative. And the monotonicity under inclusion is the strong sub-additivity that we heard about yesterday from Tadashi. It's the statement of the positivity of the conditional mutual information that if you have, well, the correlation between two systems has to increase, can't decrease as you increase the systems like this. Okay, so if you saturate this sub-additivity, so there is mutual information is 0, that means that the corresponding reduced density matrices, these marginals, actually decorrelate completely, factorize. The density, the common density matrix factorizes like this, so there is no correlation. And so that is the term that this is what is referred to by this marginal independence. these marginals are independent because the common thing factorizes. Okay, so marginal independence just means saturation of this mutual information. Okay, so now in the bulk, how do we think of this? Well, just to remind you, we already heard this many times, the entanglement entropy for static configuration. I'll just be considering static configurations for the entirety of this talk. For static configuration, you can write the entanglement entropy as the proper quarter of the proper area of the minimal surface that's homologous to this bulk, to this boundary subsystem. And the homology region, which I'll be sloppily, for sake of brevity and familiarity, just referring to it as the entanglement wedge, although it's just a slice of the entanglement wedge. Okay, so the entanglement wedge of a joint subsystem, AB, let's say, is disconnected when the mutual information vanishes generically, and conversely, it's connected when the mutual information is non-zero. In particular, it can only be positive because we know that it has to be non-negative. Okay, so when the mutual information is positive, the entanglement wedge is connected, and conversely. Okay, so the if and only has to be qualified, so we did that in this paper, and also explained that that extends to multipartite informations for the experts here. So, you know, multi-component entanglement wedge is connected if and only if you have this non-zero multipartite information. But here we'll just deal with the mutual information, because any multipartite information you can express in terms of just mutual informations. Okay, so let's just stick to mutual information. Okay, so this pattern, well, all right. So this marginal independence, if I specify which subsystems are correlated and which are decorrelated, we call that the pattern of marginal independence. Okay, so it's just the pattern of marginal independence just means a specification of all the pairs of disjoint subsystems for which the mutual information vanishes, which means equivalently the pairs of subsystems for which the common entanglement wedge is disjoint. Okay, so we'll translate the problem of finding the holographic entropy cone to the problem of just specifying which collections of entanglement wedges can be simultaneously connected, or conversely disconnected. Okay, so this forms, in the entropy space, this PMI corresponds to a linear subspace, which is just a subspace of intersections of these hyperplanes specified by the vanishing of this mutual information. Okay, and that has a discrete structure because there's just a very specific set of these, well, the mutual informations are specific hyperplanes, specific quantities in the entropy space. So we have some finite hyperplane arrangement. And in fact, the more elements we have, that more of these pairs that are decorrelated, the simpler the system. So this is actually very nicely illustrated by, if you think of in terms of a graph model of the entanglement entropy. So let me introduce that first, and then sort of show you sort of very evocatively in picture why sort of having more stuff decorrelated simplifies the system. So these holographic graph models were already introduced almost a decade ago to sort of distill the geometrical information that goes into building up the entropy vector into a much simpler, manifestly discrete structure, just a graph. So the prescription for building a graph is you specify the boundary configuration, the set of regions and the boundary state, and you draw all these entanglement wedges which partition the bulk space, and then you have a vertex of the graph for each cell here. Okay, so here we have, for example, entanglement wedge of AB, which partitions the entanglement wedge of BC. So we have two cells here that each get a vertex, and so forth, plus, so you have a bunch of these vertices, and you put a link, an edge between, for each adjoining set of regions. And the edge weight for such an edge is just corresponding to the area of that corresponding part of the RT surface. Okay, so that allows one to then calculate the entanglement entropy of any subsystem by just a min cut on this graph. Okay, so I'm not going to get into details of how you compute it. We don't need it. There's a correspondence between, any bulk configuration you can distill into a graph. And from any graph, you could construct some bulk configuration. So this holographic entropy cone coincides with a graph cone. Okay, and by the way, just as a small aside, whenever you have an intersecting set of RT surfaces, that the initial graph has these cycles. All right, so now let's look at n equal to 4 configuration just as an example. So for, if you have, say, 2D boundary and you take 4 subsystems such that, generically, for now we won't decorrelate anything. We'll start with fully correlated configuration. So, A is correlated with B and with C and with D. So that means the minimal surfaces between, let's say, AC is sort of an arch, between A, B, C is sort of the triple arch and so forth. So now you ask, how do these various bulk regions, partition, RT surfaces partition the bulk? So the full graph for that is this complicated thing. It has, 81 vertices and 185 edges and so forth. So this grows quickly. This grows doubly exponentially with n. But now I want to ask, okay, so now when I start decorrelating things, say I move A a little bit away such that I decorrelate it, let's say, first from B and then from C and then from D and so forth, how does this graph start simplifying? Well, here is the chain of these simplifications when I first decorrelate A from B, then in addition from C and so forth, until at some point you just decorrelate a whole bunch of things and you end up with a very simple graph. Okay, and ultimately when you do it for, in D-dimensional entropy space, if you do it for D-1 independent mutual informations, then you end up with a one-dimensional PMI, which actually is the thing that will give us, for the experts as a preview, that will give us an extreme ray of sub-additivity cone, which is what I'm going to explain in a bit. Not for it, no, it commutes, but at the intermediate states would look different, of course. So the graphs that I've shown you, you could get different graphs if you did it in different order, but any final state you could have gotten to in any order, which it had better be the case. The PMI really is just a set of the pairs of the subsystems. Okay, so, the whole sort of hallmark of entanglement is that a perfect knowledge of the full system might not tell you much about any given subsystem, but we want to ask the opposite thing. Suppose you have a good knowledge of a subsystem, how does it actually constrain the full system? And so let me sort of organize it into sort of 3 questions of increasing simplicity. So we'll keep retreating till we get to the point that we can actually tackle. So the long-standing problem in quantum mechanics and quantum information theory is, given some collection of these marginals, of these reduced density matrices, how much, well, can you find a common full density matrix that's compatible with these? Meaning that when you trace over A, over complement of A gives you this, when you trace over complement of AB gives you this, and so forth. Okay, so that has been long-standing problem because it's hard. In fact, it's apparently in something called the complexity class of quantum Mermin-Arthur class, which is some generalization of NP hard. So that's not doable anytime soon. Actually, there's a simplification of this where you take the full system to be pure and all of these things to be disjoint, and then it actually can be, that was actually tackled already 10 years before this one, and it has nice applications to, like condensed matter. It gives you some, generalized Pauli exclusion sort of principle and so forth. So there's a nice story in that, but we won't go in that direction at all. Now, a more promising looking thing, which we also won't solve, is suppose instead of being given the marginals, you're just given the entropy vector. So that's just a single quantity for each of these marginals, okay, just a single number. Can you then specify some density matrix and configuration that implements that entropy vector? So if the answer is yes, then we will say that such an entropy vector is realizable within that given system. All right? And then what we will actually retreat to, the problem that I want to talk about is what we call the marginal independence problem, of just saying, given the specification of which systems are correlated and which are decorrelated, given this PMI, does then there exist a full density matrix and configuration implementing that? Okay, so this marginal independence problem, well, you can specify in various contexts. In quantum mechanics, is there a configuration that implements in quantum mechanics that we dub this quantum marginal independence problem? If you restrict further to just geometric states in holography, then that's the holographic marginal independence problem. And in fact, we'll retreat even further on and just ask about one-dimensional PMIs. Okay, so we'll call that extreme holographic marginal independence problem. Okay. This is a pattern of marginal independence. Okay, it's just a set, it's just the specification of what is correlated and correspondingly what is decorrelated. Okay, so this, of course, not all patterns of marginal independence are possible. I mean, there's a lot of them, right? So there's 2 to the number of different mutual informations, and that's the number of mutual information scales as Stirling number. So with n, it's like n 3 to the n, so this would be like 2 to the 3 to the n, with some higher exponents. So this is huge, but most of them are not realizable, either because of a mathematical inconsistency or physical inconsistency. What I mean by that is, a mathematical inconsistency would be that it's just, there's many redundancies or linear dependencies between the different mutual informations like this. And so if just 3 of them are 0, the other one must also be 0. If you have, but we also know, for example, by subadditivity that everything is non-negative. So if these 2 are 0, then automatically these 2 must also be individually 0. But you have stronger statements. For example, SSA imply, this would be called Klein condition, that if you have 2 systems which are decorrelated, their subsystems must also be manifestly decorrelated. And this actually ends up being very powerful. So a useful sort of organizational principle is to sort of collect these mutual informations by endowing them ordering, so collect them in a poset structure. So this would be, for example, for n equal to 2, a structure that explains, okay, I2 of AB is included, is related to ABO because B is in BO and so forth. Okay, so it turns out that this Klein condition then specifies that if you have some subsystem in the PMI, then it means that its entire downset in this poset must also be in the PMI. And this is very restrictive. Okay, so the linear dependence is going to be taken care of in a moment geometrically by just associating a PMI or defining PMI as a span of a face of a subadditivity cone. Okay, I'll get to that momentarily. And this Klein condition then tells us that this is a downset. So it reduces the number of possible, already reduced by this linear dependence, possibilities for PMIs much further. So for example, for the one-dimensional PMIs, you get this drastic reduction by insisting that it has to be a the set has to be a downset in this poset. All right. So now let me turn the page and talk about the geometrical picture of these things in entropy space. So that gets to the entropy cone. And so you can think of the entropy cone as a collection of all admissible entropy vectors. So in holographic context, the holographic entropy cone is all the geometric states in the entropy vectors corresponding to these geometric states in holography. And you can characterize it by these holographic entropy inequalities, which are the facets of the cone, or by, complementarily by sort of the extreme rays whose convex hull determines the cone. And we'll be mostly focusing on this picture. But in fact, it's useful to consider a whole, collection of cones, a hierarchy of cones. So I already specified the holographic entropy cone. You can enlarge that to the quantum entropy cone, which is just a collection of all physically realizable entropy vectors. And you can also consider this quantity I have been mentioning, this what I call the subadditivity cone, which is simply the collection of all entropy vectors which are compatible with all instances of subadditivity. Okay. Again, this will be the key player. So there's this nesting. This cartoon is supposed to just specify that evocatively that, subadditivity cone is polyhedral. The holographic entropy cone is also polyhedral. The quantum entropy cone we don't know. We know very little about, but it's clearly nested between the two. And in fact, you can find further cones that are nested in between them. So for example, you can have a cone that's all entropy vectors compatible not just with SA, but SSA as well. Okay, that would be somewhere in between. It might even coincide with the closure of the quantum entropy cone. We don't know. You can also take just the convex hull of the subadditivity cone extreme rays, which are holographic. So that would be a subcone in this holographic entropy cone, and so forth. So both of these actually will, I'll mention later if I don't run out of time. So for two parties, if you just partition the system by specifying two parties, all of these things coincide. But for larger, more refined system, they are very far apart. Again, this gets greater with larger n. Okay, so I don't have time to go through how we sort of obtain the holographic entropy cone from the subadditivity cone, but the upshot of using, in this paper, of using these graph models in holography and subject to a conjecture that, well, a stronger one that we need would be that all extreme rays of the holographic entropy cone can be described by tree graphs. Subject to that conjecture, which we have a lot of evidence for, but no proof, you can prove the following fact, that every extreme ray of this holographic entropy cone at some number of subsystems n can be obtained from extreme ray of subadditivity cone for a more refined system, for some larger n prime, as a projection. Okay, and so that means, so let me show you in cartoon. So here I have organized by n the sort of sketches of these cones. The subadditivity cone is the largest one. The holographic entropy cone is this orange bounded thing, and the dark part of the orange bounded thing is just the convex hull of the extreme rays of the subadditivity cone. So for small n, all the extreme rays of the holographic entropy cone are simultaneously extreme rays of the subadditivity cone. But there's some n already at n equal to 5 that the extreme rays of the holographic entropy cone need not be extreme rays of the subadditivity cone, but they can be obtained by coarse graining an extreme ray of, this one of the subadditivity cone for a more refined system, for a larger n. And different ones might be needing different n, but once you go to the sufficiently high n, all of the extreme rays of the holographic entropy cone here can be obtained from the holographic extreme rays of the subadditivity cone up there. Okay, that's the main content of the theorem. All right, so that means it's in practice, it's in principle, you can reconstruct the whole holographic entropy cone if you know the extreme rays of the subadditivity cone, which are realizable. In practice, that's complicated, but in principle, it sort of demystifies that structure. And so then the crux is, how does one find this requisite set of holographically realizable extreme rays of the subadditivity cone at larger n? How much time do I have?
About 5 minutes, 6
Great.
minutes.
Okay, thank you. Okay, so it's useful to sort of think of the whole set of extreme rays of the subadditivity cone. Okay, I'll call that by this undecorated symbol. And then look at the various subsets of them. Okay, so you can look at the ones that are compatible with this Klein condition, that, you know, if two systems are decorrelated, their subsystems are decorrelated. Okay. You can look at the ones that are furthermore compatible with SSA, which is a stronger condition. You can look at the ones that are compatible with, that are realizable in some quantum system, and finally the ones that are realizable in holography. Okay, so this is the thing that we finally want, and there are nested sets like this. Now, in fact, for n equal to 2, they all coincide, everything coincides. But for larger n, this is definitely, as I showed you in these two tables, this is definitely much smaller set than the whole set of the extreme rays of the SA cone. But it's still true that by explicitly looking at what these sets are, up to n equal to 5, that's known completely, well, and now at n equal to, okay. So up to n equal to 5, we can check that all of these things coincide. So initially we were hoping that maybe there's some deep reason that all of these things coincide for larger n as well. And if that were true, then that would give us a handle on the quantum entropy cone without knowing anything about the quantum entropy cone by sandwiching it. That doesn't turn out to be the case, unfortunately. That fails already at n equal to 6. But that motivated us to find explicitly the set of 6-party subadditivity cone extreme rays that are compatible with KC. And we accomplished that, although we haven't yet finished writing it up. Okay, so, and the process is not quite non-trivial, and I think it's not very hopeful to go, you know, beyond that, but you need to nudge it quite carefully. But one thing that is of great help is to utilize this poset structure and insist on, you know, linear dependence, this Klein condition implemented by the downsets, and further tricks. Okay, but the upshot of that was that, okay, so there are 220 orbits under symmetry, thank you, that are compatible with the Klein condition, but 12 of these actually violate SSA. So SSA is not well, KC is not full approximation to SSA, it's just reasonably good at this so far. So the remaining 208 orbits that are compatible with SSA, which amounts to like 500,000 of individual extreme rays, if you unpack the symmetry orbit. And in fact, not all of these are holographic. Okay, so there's already a gap. So 52 are violating some holographic entropy inequality. But some of these actually can be realized by a hypergraph. I don't have time to go into explaining that, but the upshot is that hypergraph cone is inside a stabilizer cone, which is inside a quantum entropy cone. So these states are realizable quantumly, but not holographically, and so we also have a gap between the holographic entropy cone and, between the set of extreme rays of SA cone that are holographically realizable and that are quantumly realizable. Okay, so, but we have explicitly constructed graphs for 141 of these, and so we know that all of those are in this set. There's few more that we haven't yet, that don't violate anything, but we haven't yet constructed graphs for, so we don't have a complete characterization yet, but I think we're pretty close. Okay, so this is example of the ones that are realizable graphically. They're nice tree graphs, which are, well, not that simple, but not that complicated either. And here are examples of the ones that are realizable quantumly, but not holographically. And in fact, it's, even though we don't know how to do the systematic analysis for higher n fully, we can generate extreme rays of subadditivity cone for much higher n by sort of guessing the structure and then checking that they're extreme rays. So for example, this gives you an entropy vector that's an extreme ray of the subadditivity cone for n equal to 9, okay? And you can use that to actually put inner bounds on the quantum entropy cone at lower n. Okay, so this is a paper that appeared last December where we explained this point. We use these extreme rays of the higher n subadditivity cone to because when you project, you can't project outside of the cone. You always project inside of the cone, so it gives you an inner bound. And we obtain the entire quantum entropy cone at n equal to 3 and the entire stabilizer cone at n equal to 4. So this could in principle be actually quite powerful technique to use for putting bounds. If you put, we already know a nice outer bound on the quantum entropy cone. If you can make the inner bound approach that, then we would nail it, again, without any explicit construction for sort of more complicated quantum states. All right, so let me just summarize. I'm almost out of time. So if you know the entire, this holographic entropy cone can be reconstructed from this much more primal structure, the subadditivity cone, once you know which extreme rays are holographically realizable. And so if you know the entire, if you have solved this holographic marginal independence problem for all n, you automatically, in principle, know the holographic entropy cone for all n. Now, if you look at the inequalities that are the facets of this cone, they look horrendous. Okay, another completely different branch of the story is that we have also simplified many of these at n equal to 6. So we have almost 2,000 of these orbits of entropy inequalities at n equal to 6. But they don't have a nice enough structure to have a narrative for what they mean operationally. But they follow from just this sort of construction. So it's a sort of dual way of looking at it, and in some sense demystifies a little bit of, the complication comes mainly because you have fixed n, and so there's all these sort of new, number theoretic complications cropping in from that. There is nothing fundamental about fixing n for a continuum system, so it might be sort of a, red herring to sort of, be worried about the complexity of the form of the holographic entropy inequalities. Now, the ingredient, apparently there's very little ingredient that was fed in from holography. The subadditivity cone certainly knows nothing about holography. The only thing that we used was, well, which ones are holographically realizable? But we have used the fact that the boundary lives on a continuum, so you can arbitrarily refine the space. And also, we have used this construction that the RT prescription, where for the classical picture, you have phase transitions between sets of RT surfaces. And that was a sort of crucial ingredient. That's the thing that sort of helped us use this trick of this pattern of marginal independence and all of that machinery. Okay, so we have seen a rich structure of the subadditivity cone. There's a huge gap here, small gap here, and we would like to explore further, all this nesting of these various interesting subsystems. And so I'll end with a question, which is, for what classes of systems might it be that just knowing the pattern of correlation and decorrelation, you can actually obtain the full entropy cone pertaining to that subsystem, as was the case for the holographic class of states. Okay, so we saw, so if X is the holographic subsystem, then the holographic entropy cone was determined by the holographic realizable set of extreme rays of the subadditivity cone. Could one potentially play this game for just the quantum entropy cone as well? Okay, so with this provocative question, let me end here, and thank you.
Thank you very much. Questions?
Great. Okay. Thanks, Veronika. So I'm curious about this thing you said about the pattern of marginal independence being used to organize your way of thinking about entanglement in more general systems. So in holography, we have this large parameter, 1 over g Newton, and the decorrelation is, there's 0 mutual information at order 1 over g Newton, but there secretly is order 1 correlation between any systems. So I'm wondering how you think in a general many-body system where you might not have some parametric separation of scales and entanglement, you might be able to use this idea of marginal independence.
Right. So, well, it's easier to retreat to just let's say, finite quantum system with a bunch of qubits, and then you can decorrelate them completely. For quantum field theories, you do have you don't saturate mutual information. It's bounded from below by a correlator, but which is generically non-zero. So indeed, my hope would be that even in that context, you could try to somehow do it at some approximate level. Okay, you can separate, I mean, if you have large n, you have certainly separation in scaling with n, and you can talk about just the leading part. And then, I mean, as you probably know, even for this quantum marginal problem, you have this the systems which are pinning exactly, but there could be, you know, quasi-pinning that you're very near a boundary, but not exactly at the boundary, and it's still, you know, the whole machinery still sort of goes through. It might be something like that in this context here.
Thanks. So you explained the sense in which the mutual information captures the connectivity properties of the bulk. And something you might ask for is the full homotopy type of the bulk. So is there any sense in which higher order mutual informations might capture higher homotopic information? Maybe you could fill a graph into some sort of cell complex structure?
What do you mean by higher order mutual informations?
Like these I3s and things?
Multipartite information.
Yeah.
Yeah, so multipartite informations we do, okay, so one comment to re-emphasize is that all of them can be expressed in terms of the mutual informations.
Yes.
And so we have all the information that the multipartite informations are telling us. Now, it might be that the multipartite informations are somehow more convenient for the packaging. Their number grows faster. Okay, so at large n, the number of I2s grows as 3 to the n, the number of I3s grows as 4 to the n, and so forth. And so it's this higher Stirling number. So there's a trade-off. And so we sort of didn't find, I mean, you might also ask, another enlargement you might ask about is conditional mutual informations rather than mutual informations. And that again grows as like tripartite information that grows as, you know, there's many more of them because you have more sets of systems to specify. And we haven't yet found that to be sufficiently, to be convenient enough, or it's so much more messy that we haven't found the utility to overweigh the messiness. But we haven't really, I think it's fair to say that it should be explored a little bit more, because it may well be that, you know, you can find a little bit more convenient packaging that actually does simplify things.
Hi, Veronika. So is it true that if a typical state in a quantum system will live on the extremal rays of the holographic entropy cone?
No. Typical state will be far. So the extreme rays are very special.
Very special.
Very special. They have the property that they can't be obtained at conical hull of any other states. That's why they're called extreme rays. Mm-hmm. And so, yeah, the generic state will be sort of more somewhere in the middle of the entropy cone. Or maybe, I mean, depending on what you, like if you have a system in holography and you have a bunch of, let's say, single boundary and you have a bunch of small regions, certainly sets of them will be decorrelated if you just sprinkle, you know, blobs on a in the boundary. And so then those will be on the boundary, somewhere on the boundary of the holographic entropy cone, because they will be saturating some subset of mutual informations, but still a much larger dimensional subspace than the one-dimensional subspace required by extreme rays.
I see. So if I just have a hard random state, could I study what type of where it sits in this?
That would be interesting. Yeah, I think that would be interesting exercise. So we have not done that, but I think that
should
would
be inside of the holographic cone instead of the quantum.
It might well be inside that, yeah, because it's, I mean, you see, the whole structure is permutation symmetric under exchanging the labels and also under exchanging the purifier. And so both sets of cones, but you might think that the hard random somehow implements this more manifestly symmetric. So it sounds like, to me, that naively sounds like that would definitely be inside the holographic one, but that's just That's just a guess. Yeah, you should think
Thank
about
you.
it more.
Are there? Oh, yes.
I was wondering whether these inequalities can be combined with some expected dependence on the geometry of, let's say, the regions that are distant or something, let's say in the vacuum state of conformal field theory, to actually bootstrap these things quantitatively.
Yes. So that actually, well, okay. So the jewel of this story that I haven't told you is sort of looking directly at these holographic entropy inequalities. And there's there's very tantalizing structural relations between smaller n1s and larger n1s that look like you could indeed build them up. One useful observation for this exercise is any holographic entropy inequality at some n, if you trivialize over some subsystem, has to reduce to a true quantity, true inequality for the smaller n. And so you could try to build that in constructing the higher n1s by insisting that it has to satisfy all the smaller n inequalities, and already try to build that into the form. Okay, so I can tell you, I mean, that's a nice sort of longish story, so that, but I can tell you sort of a little bit more about that offline if you want.
I think one final question.
So is there any consistent pattern in the graph representation of the states which appear on the extreme rays for different ends?
Consistent what pattern?
Some pattern in the graph representation, like if they're not random.
Well, so if they're fully correlated, so at n, so the number of regions would grow, so it's a doubly exponentially with n. So like at n equal to 5, you already have over 2,000 vertices. By the time you're at n equal to 8, it's like 10 to the 20. And it has only been even solved how many you have up to, I think, n equal to 8 or 9. Now, once you start decorrelating subsystems, the ones that we know for sure have to be decorrelated for all the extreme rays are all the singleton mutual informations. But that itself doesn't help you sufficiently because there's still many more left at large n. But basically, the exercise is to keep decorrelating stuff in this MI poset downset structure, grow the downset in such a way that you get all the combinations, and that gives you all the extreme rays. But at the level of the graphs, you can see the graphs, as I showed you in the sequence of things, the graphs really do simplify even faster than, by the time you would get to, this is still not at the extreme ray because, this would be in 15-dimensional space, so you would need 14 of them, so we're not there yet, but already the graph is quite simple. Yeah, so there's various, I can tell you what these things look like at higher n. Basically, each time you add a party, you add all the sets of RD surfaces for all the subsystems that now involve that party. And each of those RD surfaces cuts a whole bunch of other RT surfaces that were there for all the crossing regions. So basically, it's like for each such thing, so for each of the n parties, you duplicate the structure. Okay, that's why it grows so quickly.
Okay, in lieu of time, let's close the discussion here and thank Veronika. And then let's